Good morning everyone and welcome to this online lecture on the smart grid architecture model. Before we start, I would like to introduce myself briefly. My name is Christian Neureiter. As you already can see, I am working at Salzburg University of Applied Sciences, and my main task here is to work at the Josef Ressel Center for Dependable System of Systems Engineering, where we are working on concepts and methods on how to enable the development of dependable system of systems in an interdisciplinary scenario. Our company partners are Bosch, Siemens, ChargePoint, and GeoConsult. And if you're interested, just browse through our homepage and learn what we're doing. The learning goals for this particular lecture are to understand the motivation behind it. So why are we thinking about how to develop dependable smart grids? So what are the challenges? Then we would like to introduce some of the fundamental concepts like model-based systems engineering as methodology or as mindset even, and the smart grid architecture model as theoretical grounding of all this work. And the third learning goal is that you understand the idea of how we are going to apply the SGAM for smart grid architecture development. This lecture is structured in two parts. Each of them takes 2 units. In the first one, we want to cover some background information and discuss the fundamental concepts of SGAM. And in the second one, we're going from theory to practice, which means we demonstrate how to apply SGAM in architecture development. And on this basis, today's agenda looks like this. We want to start with some introduction to clarify the background again. Then we want to motivate everything what we're doing with a more profound discussion on the individual challenges in the smart grid engineering. Then we step a little bit back and we start the fundamental consideration. What is complexity and how to deal with complexity before we're going to introduce the smart grid architecture model. And that's mainly it for today. Okay, so first of all, let's talk about the motivation, why we're doing this, and what are the particular challenges we're facing in smart grid engineering that we want to address with our approaches. So just as a brief recap, what is the smart grid? Well, the smart grid is the electricity network, our power grid, which is complemented with digital technology that enables us to better integrate renewable distributed energy resources. And so they give us a better control option for the whole power grid. The challenges that we are facing in here can be separated in, first of all, the overall increasing system complexity, which I think is pretty clear. Then this doesn't even stop with complex system. It also goes beyond as we see a system of systems. We will talk about this in a minute. Then the second challenge is the interdisciplinary development. As you can imagine, you have power grid engineers on the one side that have to cooperate with software or ICT engineers on the other side, and even business guys. And that could be kind of complicated, as you can imagine. And the third challenge, which comes overall, is the fact that the power grid is a part of the critical infrastructure. And as such, we have pretty strict dependability requirements that we have to meet all of the time. So one by one, let's start a brief discussion about all these systems. First of all, what does complexity mean? So there are different publications about complexity. For that reason, I would like to highlight which one we are using. So we rely on the definition from Haberfellner et al., which is originating in the field of systems engineering, and they make a fundamental separation of systems on basis of two different axes. On the one hand, they consider dynamic and alterability of a system. which means do we have a stable system structure or do we have a system structure, a topology that changes while in operation? And the second one is, I have to move to the side a bit, is diversity, variety, scale, which means we are considering the size and the amount and the diversity of the constituting systems. And on this basis, we can separate between four different systems, like simple systems, two different types of complicated systems, the massively interconnected ones and the dynamic ones, and finally, complex systems. And I'm talking about this because this is not just a scientific classification, rather this is a fundamental separation that should guide us choosing our development approach. So this means the classification of a system is the basis for selecting how to approach the engineering task. For example, let's consider a simple system. Let's say we have an electric circuit, like a low-pass filter or an oscillator. Then we are able, with analytic engineers know-how, here we are able to make a prediction on some bandwidth frequencies or anyway. So the idea is, if it's a simple system like an electric system, a small one, we have engineering know-how and we can deal with it. But if we think about a bigger system, like the whole power grid, then probably it's pretty hard for us to make an exact calculation on the exact voltage that we have at the outlet right now with 2 digits after the comma. Yeah. And I'm pretty sure not even the DSO, the distribution system operator, is able to make the exact calculation, because the underlying system, there are so many constituting elements. So as you probably can guess, we are here now, and there are so many involved components that it's pretty hard to make an exact calculation. So instead of making perfect calculations, we rather rely on statistics. Like for the operation of the power grid, we are considering what is the typical consumption as a day like this, and that's the basis for planning of our operations. So you already see, depending on the diversity and the scale of our system, we can separate between the analytic approach, where we make calculations and formulas, and the statistics approach. And if we go in the other dimension, then we could, for example, think about an ICT-based system where we have mobile clients communicating with a server. So the difference to our power grid here is that the power grid, as we know it today, has a pretty stable structure. So it doesn't change every day where the wires are drawn. And in contrast, our ICT-based system, like some mobile phone with an app and a backend server, there we have permanently new connections and disconnection of existing connections. So our structure is not stable in that context. And that's what we call a dynamic system, where we have to consider different changes, like load balancing, update services, and so on. So you already see, again, the classification of the system helps us indicating the challenges that we have to face. Yeah, and finally, if we consider our power grid again, and let's assume now that in our power grid, we have dynamic connections as well, which could be electric vehicles that are connected on the one hand and disconnected on the next day. Or we could even think about the significance of individual connections, like how much energy is produced from some renewable energy source or anything. Then we are approaching a complex system, which raises the question how to deal with complexity. And to make it a little bit more challenging, the example I've chosen, the power grid, is not only a complex system, rather it can be characterized as a system of systems. And the system of systems as such is characterized by the so-called Mayer-De Laurentiis criteria, So the idea is that we have individual systems, like for example, a power grid and a vehicle. And these two individual systems, they agree that together they would like to achieve a higher goal. For example, let's say we want to improve our environmental protection. We would like to improve to increase the share of electric vehicles, and we would like to achieve a better utilization of the power grid to enable more electric vehicles to participate in the grid. Now, that's our superordinated purpose. We would like to improve the grid as a resource to enable more vehicles to be part of this game. And so the power grid and the electric vehicle have to move to the side a bit. They could decide on something like, let's use flexibility. So the power grid says, well, when I see that I'm running short of my grid resources because too much power is consumed or something, then I could ask some of the participants in the grid, like the electric vehicle, for flexibility. And the vehicle on the other side says, well, if I'm connected in the evening at my parking lot, then I only want to be fully charged in the morning, but it doesn't matter if I'm charged at 2 o'clock in the night or 3 o'clock in the night. So I could offer flexibility for a better price. And so this is the basic agreement between the power grid and the vehicle. The power grid says when I'm running short on grid capacity, I'm asking the car for flexibility, and to motivate it, I will offer a better price. That's what we call an incentive. And so we have a good agreement, and that would work to improve the grid utilization. But that's only half of the truth. So in reality, let's imagine a scenario like following. Let's say it's, I don't know, 6 o'clock in the evening, I come home with my electric vehicle, and I put it to my charging station. The car is charging, everything is fine. And then it's 8 o'clock in the evening, everyone turns on the TV, maybe it's cooking, energy consumption is rising. And so the power grid says, I have a pretty high energy consumption right now. Let's increase the price. And my vehicle recognizes the increase of the price, and it says, well, I better stop. I make a pause, I go on hold, and I wait for a better price before I continue charging. Everything is fine. And 8:30, my wife comes back home, and she has also an electric vehicle, and she puts it to the charging station. And her vehicle detects that the price is pretty high at this moment, and it goes on hold, and it says, let's wait for a better price. Then it's 9 o'clock p.m. My daughter comes home with her electric car. She puts it to the charging station as well, and again, her car realizes that the price is high, and it says, let's wait. So right now we have 3 electric vehicles attached to the charging station, waiting for a better price. And then at 10 p.m., when TV is over, everyone goes to sleep, power consumption reduces, and the grid says, okay, let's decrease the price again, and the price is going down. And the consequence now is that at this moment, I have many electric vehicles waiting for a better price, and all of them start charging simultaneously. So what happens now? We have the power consumption, everyone starts charging simultaneously, so the power consumption increases rapidly. The consequence is that maybe the power grid now says, oh, that's a pretty high consumption, let's increase the price again. And the vehicles see, oh, the price is high, we all turn off again. And in that moment, maybe not only the vehicles turn off, maybe the price increase is very high because it's a steep development here. And also the heat pumps say, ooh, now it's too expensive. I wait for a better time. And in that moment, when all those consumers at the same time drop off, when the power consumption drops again, then we have too much energy in the power grid. And the consequence again is that the power grid says, oh, panic, there is so much energy, I have to get rid of it. And again, the price. And so what we see in the end is an oscillating behavior that we definitely don't want to have in the power grid. And this is what we call an emergent behavior. So no one is the single producer of this behavior, but this behavior is something that we can observe in context of a system of systems. And this is exactly what we need to deal with, or what we see if our system is characterized as a system of systems. Yeah, and why is it so important to handle this? Well, the superordinated goal, as I already mentioned earlier, is that our power grid is a so-called critical infrastructure, and as such it has to maintain pretty strict dependability requirements. And just to recap this term, dependability itself is just an umbrella term, and it covers the different terms as we see here: reliability, availability, maintainability, safety, and security. And in context of the power grid and many other services today, we also suggest to also maintain privacy, or to also consider privacy like data protection in its context. So what do we have so far? We have learned that the power grid is a complex system, or even a system of systems. We have learned that this system needs to maintain strict dependability requirements. And now we want to take a look at how to deal with complexity in general, to derive an approach how we can handle complexity in engineering of power grids. By acknowledging that complexity is the challenge that we have to overcome, it appears valid to think about how to deal with complexity in general. And for that purpose, let's start off with a small experiment. So take a good look at the picture behind me and look, how many O's do you see? How many O's do you see now? And what you probably experienced was the following. When you were looking at the first picture with 4 O's, then probably you have not been in need to count. You take a look and you will immediately see it. It's 4 O's. If you take a look at this picture with many, many more O's, then probably you do not see it on one view how many O's there are. So you have to count, or if you are clever, you make a multiplication. You count the horizontal number and the vertical number, and then you multiply them and hope that the rest are all O's as well. So why is it that way? This one is can be argued on basis of something that is called Miller's law, who already developed in 1956. He was a psychologist from Harvard. He developed a so-called magic number, and he identified that our brain has a capability, we have a cognitive capability of around 7 elements that we can process at the same time. That's the capacity of our brain. So we have a cognitive limitation in our human brain. The real world, on the other hand, where we are living in, is obviously more complex than just 7 elements. So the question is, how is our brain able to deal with complexity that is bigger as something that we can process in one step? And the answer is pretty obvious. Our brain is applying 2 tricks. One is called abstraction, and the second one is called separation of concerns. And with these 2 tricks, we are able to deal with the real world complexity even though our brain is only able to process around 7 elements at the same time. Let me illustrate this. First of all, if I'm giving a lecture and it's not a remote recording like this one, but I'm standing in a classroom and I look to the audience, what do I see or what do I perceive? I'm not perceiving a wall of atoms, even though someone could argue in front of my eyes there is a wall of atoms. Some of them contribute to air, some of them to people, and so on. No, what I'm perceiving is a bunch of objects of type human. So that's the students in front of me. They are objects of type human. And if I'm going into interaction with one of these students, like I'm concentrating on one person, I'm going one level closer and I see this one person and I perceive a head, a body, arms and nose, arms and legs. And if we start arguing and I go even closer, face to face, then I probably see eyes, nose, ears, mouth. So I'm always staying on an abstraction level that I can handle. And I'm handling this level on about 7 elements, on the basis of 7 elements. So I'm decomposing every object that I perceive into 7 elements. And if I need to go into more detail, then I'm changing the abstraction level and no longer concerned about the other elements around. So that's the concept of abstraction that our brain is inherently using to deal with complexity. The second trick that our brain is able to do is called separation of concerns. So, for example, if we assume that, let's assume we are automobile fans and we like the Porsche 911, which is a sports car, and we go into we go to the car dealer and we see this brand new car and we are looking at the car and we are looking at aspects like, for example, the color, the horsepower, interior, exterior, maybe the price, aspects like that. That's how we look at this one object. And then if we want to drive home, and in my case, I would enter my Volkswagen Caddy and I go up the Deutsche Autobahn, German Autobahn, and I want to enter the Autobahn, and there is a Porsche coming from behind that is very fast. What am I looking in this moment? I no longer care about interior, exterior, price of this car. I'm only concerned about the current speed. Will he crash into me? So that's what we see here is in both scenarios. We look at the same object, but depending on the situation, we choose a different focus. So we have a different concern. And so we are choosing our focus on basis of this concern. And that's what we call separation of concerns. We handle one concern after the other. And if we put these two things together, these two magic tricks, then we end up in something that is called a mental model. And that's exactly the way how our brain is dealing with complexity. It is establishing mental models, which means it applies the two paradigms, abstraction and separation of concerns. And if we switch to our engineering perspective and we think about the fundamental definition of a model, then we will see that a model is the abstraction to relevant aspects, which basically is exactly the application of these two magic tricks that our brain is applying to handle complexity. So this is pretty good news because now we found a fundamental principle that helps us to decide how to deal with complexity. The answer is we use models. But that's only half the truth again, because in the end, we also have to think about which type of models are we using. So let's take a closer look. For example, This one here is a model. On the right-hand side, we see a real person. On the left-hand side, we see a simplification, an abstraction to relevant aspects. In that case, it is a model. You all know it's a former American president. I don't need to name him. And probably you also will realize where I took this picture from. It's from The Simpsons. So obviously, here is a model. We recognize who is represented, and we know the language where the model is coming from. And now let's take a second look. Who is that? I guess the younger audience will have a hard time figuring out who it is, and the older audience probably will recognize him. Yeah? If you're not sure, you can Google the Watergate situation, then you will find out the name of this guy. To say it, it's Richard Nixon. So it's a former US president taken from The Simpsons. The first one probably you did recognize, the second one you didn't. And the answer why this happens is that understanding of models always requires a common context. Right? So a model requires interpretation, and the way how interpretation works depends on the context. And the context could be in an engineer, in that case, it could be your age, your daily experience, like Donald Trump plays a role in the daily news, not so much anymore, luckily, but Richard Nixon doesn't play a role. So in our life context, Donald Trump is recognized, Richard Nixon isn't. And the same thing is true for technical models. So if we think about engineering models or models in general in the smart grid, we realize that there are many different models that are being used. We have something like, we have physical models like electrical models, or we have control systems models, we have architecture models, maybe UML and SysML. We have maybe some enterprise architecture, some context models, and so on. But what we already can draw out of this is that whenever we want to apply modeling to deal with complexity, we first need to answer the question, which types of models that are being suitable to be used in the different contexts that we see here? Or is it possible to find one model that is usable for everyone? So we already learned that models are a good approach to deal with complexity, but now we have to answer the question, which kind of models, which type of models? Is it something new, something everyone needs to learn, or how can we approach that? And to answer that, I first would like to go to the whiteboard and make some initial discussion on some fundamental aspects on technical models. So let's move over to the whiteboard. Here we are. And let's think about the following situation. Let's say we want to build a house. We're planning a house. And in our new house, we are considering the energy system, the thermal energy system, like the heating. And the first question that comes up with that is, how much thermal energy do we need to bring into this house to keep it warm? And the answer is pretty simple. We have to bring in so much thermal energy as we are losing to keep it constantly warm. So to be able to answer this question, we first need to understand how much thermal energy do we lose. And this is done on basis of some analysis. Yeah? And every analysis starts with a good model, like for example, this one. I just make a sketch. It's already a model. It's the abstraction to relevant aspects. Not very pretty, but I think you get the idea. And this is a wall. Now we want to understand how much energy we lose. So first of all, we need to find the cause-effect principle, which in that case is a stream of heat going from the inside to the outside. And now we need to understand how much energy we are going to lose. So a specialist from a civil engineer could go and could say, well, the value or the amount of heat that we lose is determined by different factors. So probably we have the area of the wall, we have some material specific constant, we have some disturbance here, which is the delta of the temperature, and maybe the thickness of the wall could play a role. And all in all, now we have a model of how much energy we're going to lose. And this type of model that we use here has a name. This type of model here is called a so-called analytic model. And this analytic model, it tries to answer the question, what is true? True in the meaning of, is my model representing reality? So I make, or I propose a model, and then I can verify it in an experiment or a simulate, or rather go into a simulation. And that's how we are developing our analytic model. And this type of model is also called a posteriori model. Sorry. Because this type of model is established after an effect already exists. We try to describe an existing effect. You also can call it a so-called descriptive model. As it describes something. Okay? And that's the one thing. And now let's move on. And let's say we're going to build our house. So we build the architecture. And again, we create an architecture. We create the model for the architecture. And this model could look like this. As you all know, to describe a house, we have three pictures: front view, side view, top view. Three pictures because 3 dimensions. Okay, and this model brings us to the question: can an architecture be right or wrong, true or false? And the answer is no, because we find different architectures that would fit the same purpose. So we cannot judge if the architecture is right or wrong. We just can judge if an architecture meets our purpose. And that's what we call the effectivity. So here we raise the question, what is effective? Yeah? Effective in the meaning of what meets our goals. And this type of model is what we call a so-called descriptive model, a constructive model. As there is a creational task involved. We plan to create something, and for that purpose we make a model. And this one you also could call a priori model, because the model is created before our artifact is built, or a declarative model. Because this means it's a declaration that everyone who is involved in the construction needs to follow. And so what we found here already on basis of the simple example is the fact that we have 2 different types of models that are used during construction. And if we think about back to the question for the architecture here. Is the architecture good or bad? Does it meet our goals? Then how can we understand if this particular architecture is good in terms of energy efficiency? Is there a lot of energy going out through the walls or not? And the answer is very simple, because we can simulate, for example, our construction plan in respect to its thermal behavior. And this simulation is nothing else than the application of our previously developed analytic model. So we already see the following. We have different types of models here. We have the analytic model that helps us to understand the particular cause-effect relationships. And we have the constructive model that is the basis for our plan, so what we want to build. And there is an interaction between the different models. So this already indicates something very important. Probably, even though models help us dealing with complexity, probably it's not about having one model. Probably it's about having different models and find their interaction. And with this knowledge, let's take a closer look how such an interaction could look like. So what we have for this basis is something that we call the generic modeling stack. And this generic modeling stack provides a fundamental separation of 3 different stages for 3 different types of models. And if we take a closer look from the bottom to the top, then we see, first of all, on the very bottom, we have some design models. And these design models could be models like hardware engineering, software engineering, and so on. So typically, these design models are something that are created by engineers from different disciplines, and they use their common language. And then one layer above the design models, we have our architecture models. And the purpose of these architecture models is to make a decomposition of a big system into smaller parts and units, and to integrate all the different types of models. And in that stage, we typically use object modeling. As we have discussed earlier, our brain is decomposing the complexity of reality in smaller objects and smaller units. And this is very well reflected by object-oriented design, which typically is a separation of functionality and structure. So that's the typical concerns that we have, and is done by languages such as UML or SysML. So, and with these 2 stages, we are pretty well equipped to decompose a bigger complex system into smaller bits and pieces, to model it, and everything is fine. The only problem here is that even though these architecture models are very well suited to make such a decomposition, the problem here is that people hardly understand the idea of object-oriented modeling if they don't have a background in the software engineering domain. So what we need now is a 3rd layer on top of this architecture model. We call it domain concepts. And on this layer, we need to find some models that help us to involve all the different stakeholders and to make them participate in the process of modeling. Because a model needs to be understood or used by all the people involved. And this brings us, or this further details our quest for the models in the way of how could a model on this level look like. And to identify how something on that level could look like, let's go back to the analogy of how to build a house. And you remember, in the ancient times, people were planning houses or cities like this. And today, typically, we are no longer drawing with pen and paper. Rather, we are using CAD, computer-aided design tools. And here, maybe we can find some answers. So let's take a look how modeling of buildings work. So first of all, what we need is we need to have an agreement on different views that are needed for the development of our houses. Like, for example, as we mentioned before, the architecture views in the house cover typically the front view, the side view, and the top view, roughly. And further, we want to integrate different aspects depending on the particular concerns. Like, for example, we could use some models for electric wiring or for the installation. And these symbols, they follow a particular terminology. That's what we call a model kind. So we have the views already, which build the frame, like the top view, and then we have the integration or the depiction of the views on basis of model kinds, which is a common agreed taxonomy. And in the end, we don't want to use pen and paper because that comes with some difficulties. Like, for example, let's assume we have this house and now we want to change this particular wall. This would the thickness of this wall. This would require us to find every single picture where this wall is depicted and change the thickness in every single picture, like here, here, or here. And with 3 pictures, this is pretty simple. But in a real project, if you have 300 or 3000 pictures, then drawing could be pretty difficult. So for that purpose, instead of drawing, we rather use CAD models, which means we have one single data object, and on basis of this data object, all these views, the same views that we are used to see, these views are projected or are projections on basis from one single databases. So, and if we change the thickness of the wall here, then in fact we are changing it in the database, and this database already poses the basis for the projections here and there. So immediately in the other views, you will see this change. That's what we call the consistency. And even more, we have some traceability, whatever that means for now. So this is the way how we are describing architectures in civil engineering. And the second thing is we don't always want to start from scratch. Rather, we would like to rely on some reference solutions, a reference architecture, like a pre-built house. And then we take a proven solution, and instead of building everything new, we rather make some customization of a proven solution. And that's the typical approach, and that's exactly what we are searching for. So what do we have right now? We have understood that our challenge is complexity. We have learned that modeling is the key because this reflects how our brain is working. And we have also seen that different types of models exist. Many of them are already set, but in particular, we are on the search for a model which enables everyone to agree on the topic. So which views do we need? Which model kinds, and how could they look like? And this picture in a more formal way can be found in the ISO 42010, which is basically the ISO standard for software and system architecture. And this gives us a very good indication how we could proceed on the search for such a model. So first of all, what we agree on is that we have a system of interest, like make it bigger, like here. We have a system of interest, and every system of interest has some particular architecture. The second thing is we raised the question how to describe our architecture. That's exactly our question. And then we can follow this path. We understand that our system of interest has particular stakeholders. And every one of our stakeholders has a particular concern. So we need to understand what is everyone interested in. And on this basis, we can specify a certain architecture viewpoint, and we can further elaborate which language do we use to illustrate this viewpoint. This could be a set of graphical symbols, such a model kind. For example, if we go back to our house, we could say I have the stakeholder who is the electrician, and our electrician has the concern, he wants to know where to put the wires in. So I specify there is a viewpoint electric installation. It's a chapter in a book or whatever. And the description of this viewpoint, the realization of this viewpoint is based on a certain model kind, like the standardized symbol for electric elements used in construction. And so we made a declaration how we are going to describe architecture on basis of the particular stakeholder needs that we have. And in the realization then, the particular design takes place, which is based on an architecture description. And this architecture description comprises different views on basis of the described viewpoints. And every view comprises a set of models. In that case, it could be a set of electric schematics. They follow the notation specified by the model kind, like the standardized schematics and symbols that we know for, I don't know, an outlet or a light bulb or a switch. Yeah, and that's the way how we proceed. That's the guideline how we can start identifying models for the smart grid. So in our case, this means what we have to do now is we have to think about, for our system of interest, the smart grid, which stakeholders do we have and what concerns they come along with, and how could we start depicting these different concerns. And that's what we do in the next chapter. Everyone who ever tried to develop a domain-specific language knows that the most difficult task is to find a common concept for communication. So if you have many stakeholders and maybe their communication is slightly different, then this can be a pretty tough task to be solved. In the case of smart grid, when the quest is to find a common concept for communication, we have a lucky punch because we don't need to find or elaborate individual concepts, because we are very lucky to have some concepts that originate from standardization bodies. And this brings the benefit that it is already agreed on. So we don't need to discuss if we make it the one way or the other. If we have a standard, then we already can say, okay, that's the basis for communication. So let's take a closer look at the smart grid architecture model, because this is something that I'm talking about that can serve as a basis for common communication. So first of all, let's talk about the background. So the background is coming from the idea that when in the smart grid, the electric domain and the telecommunication or ICT domain are being integrated, then probably it's also a good idea to integrate or to align at least the standards from these two domains to make sure that we don't have some gaps in standardization or some contradictory standards. So just to ensure that the standards are compatible with each other. And driven from this thought, in March 2011, the European Commission issued the so-called Mandate 490, which was covering 4 working groups with the ultimate task of identifying gaps in standardization. And these 4 working groups, They were the first set of standards team, which were browsing through existing standards. We had a process team, which was considering how to integrate use cases and stuff. We had a security team, which of course was thinking about security concepts. And we had the architecture team, which was considering how to provide a common scheme for the smart grid to enable an alignment of the different standards. And they came up with something that was called the smart grid architecture model, the SGAM. And let's take a closer look how this concept was structured. So first of all, we had one concern, which was the decomposition of the problem domain, the power grid. And for this decomposition, the guys from this working group referred to the NIST conceptual model, which is the basic and well-agreed decomposition of the power grid. So we have some generation, transmission, distribution, and in the end, a customer premises. And the guys in the working group added one more aspect, distributed energy resources. This is the only change they made. But basically, this one is the decomposition of the power grid from the huge bulk generation down to the customer. And then in the NIST conceptual model, there were three operational aspects, which is a service provider, operations, and market. And this aspect of power grid operation, so how to control this electric infrastructure, has been further reflected on basis of the so-called SCADA automation pyramid. And this automation pyramid is a very widely spread concept from industrial automation, and it separates the different stages of process automation. So what we have is on level 0, we have the sensors and signals that are close to the process that we want to control. We have programmable logic controllers, which are pretty close to the process. Then we have a superordinated SCADA HMI. Then we have the manufacturing operations management and the enterprise relation planning and logistics. So that's the typical topology that we see in automation technology. And the third aspect that have been considered in this context is the question of interoperability, which means how to make sure that two components in the power grid will be interoperable with each other. And here they use the Gridwise Architecture Council's interoperability stack, which basically states that interoperability needs to take place on different levels, like the basic connectivity, like physics, network and syntactic interoperability, and all the way up to regulatory policies and economic codes. So this is, if you take a closer look, you will find some similarities, for example, with the ISO OSI stack. But the idea of considering interoperability on different stages is nothing new, that's well established. And well established is already one of the key aspects here. All of these three aspects that stated the basis for consideration, they are well established. So there probably you won't find many people in the energy domain that would discuss any one of these things and re-ask if that's a good thing, because they are established, they are working, and most people are familiar with it. And so this looks as if it is a good basis for developing an architecture reference framework. And let's take a look what people from this working group did. So first of all, they combined the NIST conceptual model with the automation pyramid. And if you take a look what the outcome is, it's the smart grid plane that you can see right over here. And in this smart grid plane, let's switch to this, we have a grid pattern, which on the one axis decomposes the power grid from the huge generation down to the customer premises. That's the process that we want to control, the the energy conversion chain. And here we have the control axis, which basically is the hierarchical level of power system management, which means here is the ICT-based equipment and human interactions that are controlling all these individual systems. And these two things combined, the process that we want to control, the energy conversion process, and the ICT that is controlling this process, there is already value inside. Because what you can do now here is you can, any equipment in the power grid that you have, you can align inside this grid pattern. And by having a particular position inside the grid pattern identified, you already can draw conclusions like, for example, on this side, we probably have a higher need for security. And on this side, we probably have a higher need for privacy. So the position inside the grid pattern indicates requirements for your systems. And if you go one step further and you think about electrotechnical standards as published by IEC, then we have from the IEC, the International Electrotechnical Committee, we have an overview which tells you if you're here or there, then probably this set of standards is the right one for you. So that already you already can see that this grid pattern can serve as a good set of initial guidelines to identify which standards are applicable. And especially in reliable systems or dependable systems, where you have the obligation to make engineering state of the art, there is nothing better than having a set of standards from an standardization body telling you that's typically the standards that are of relevance for you. Without going further into detail of this idea, here just we can see the grid pattern helps us to structure the whole power grid and its operating equipment. And the last thing that is missing now is the topic of interoperability. So we want to ensure if, I don't know, company A makes this element, company B makes this element, and we want to make sure that there is compatibility in between. And the last thing what the guys under the mandate from M490 did is they added the GBEX interoperability stack with a little bit digestion, and they finally stated that interoperability between two elements here must be given on 5 layers, which means, of course, the physical components need to be compatible, the communication layer must fit, like using the correct and same protocols. Then we have the semantics layer, the information layer, which ensures interoperability of the data models being used. Then above we have the functional layer, which means the functional interaction needs to fit. And on top of all of that is the business layer, which guides the business objectives or the political regulation. So to make sure that two systems will face the same regulations and nothing contradictory. So, and with this one here, what we already have is we have one common picture which is used and everyone can agree on it. So it's very simple, it's very understandable, and it already gives us a good basis for depicting or structuring or architecting smart grids. Though this one has been made to identify and align standards and gaps in standardization, this framework is already very valuable to structure a whole smart grid application or a power grid. The only problem now is that this picture has been created in PowerPoint. So it's an illustrative picture and it's not suitable yet for modeling. So we need to approach this one step by step in the sense of how can we make this one applicable for modeling. So first of all, what we can do is we can already identify three things that we often find in architecture modeling as well. So on the one hand, we have some business aspects and regulation, which in a broader sense could be considered as an aspect of requirements. And then we come up with a model transformation to the next one, and we can say, okay, here we probably could have a logical or a functional model, which describes the functionality that should be achieved by one particular subsystem or the interaction of subsystems of the power grid without telling us how it is done. So this is the solution-free functional model right here. And then, as we know it from architecture development, the functionality is further transformed into technical model, which clarify which components are used, how they are connected, what's the data models, and so on. So this means we already have a concept which is very easily understoodable from stakeholders on the one hand, and which is already pretty close to typical concepts that we use in architecture development. And having this in mind, we can use the SGAM now, and we can say, okay, this is our common denominator, a common ground that could be used on this level. And furthermore, the elements here, they probably will already have a pretty good fit with the architectural models on the next stage. So where we end up with here is we need to take the SGAM as conceptual idea, as thought model, and drill it down into a set of viewpoints and model kinds, as we have already seen earlier in ISO 42010. So, and if we do it, it's a little bit a simplified concept, but here we end up with a modeling stack, where we can see we have a domain architecture model on this level, we have a technical architecture model on the second level, and down there we have the design models. And we're working on the domain architecture model. And in the domain architecture model, we need to identify particular viewpoints and model kinds to help modeling the smart grid. And if we apply the SGAM now, then we could derive three viewpoints, which are an enterprise viewpoint, which guides the requirements. We could derive a functional viewpoint, which guides the functionality, and a technical concept. And inside these three main viewpoints, we could place some particular model kinds, like the SGAM business layer in the enterprise viewpoint, the SGAM function layer, of course, in the function viewpoint, and the remaining three layers, which are technical viewpoints, technical model kinds, we could allocate them to the technical concept viewpoint. So you already see right here, this looks pretty promising. And we're able to use the commonly understood concept and to derive on this basis a common concept for modeling and communication. Please be aware at this moment that the given model kinds here, they can be aligned in the viewpoints, but they are not sufficient to develop an architecture. Because keep in mind, the SGAM has been developed for identifying gaps in standardization. And for that reason, things like, for example, a requirements model or anything else has not been considered. So we can use the SGAM for architecture development, but we need to complement it on basis of architectural knowledge. Okay, so, and where do we end up with that? Finally, we come to that point that if you remember our big picture, how to build a house, we can conclude that now we have common views. We have identified a common set of views for our stakeholders where people could agree on, and we already were able to derive particular viewpoints and model kinds, which is the basis for architecture modeling. And what is missing right now is the question, or the answer for the question, how to practically model such architectural models, which reference architecture could be used. And of course, the last one is this one, suitable for practical applications. do you have practical experiences? Yeah, that's it for today. The remaining questions will be answered in the next lecture. So to conclude the things from today, what do we have now? Again, we have an understanding of the motivation. We learned about complexity as challenge, and we learned about models that could be a good answer. We understood the fundamental concepts of SGAM, and we already have seen how SGAM could be used to derive particular viewpoints and model kinds in alignment with the generic modeling stack. And that's where we are done for today. And the next time we will answer the following questions: how to make it practically applicable in a modeling approach, and how could we build a reference solution, so which elements should we use. And I also would like to share some insights from real-world applications, because this concept, of course, has already been applied in different industrial projects in different countries. Good, that's it for today. So whenever you have questions on the topic, please don't hesitate to contact me. Here is my email address, and I'm always happy to answer questions, to get in contact with you, and also to get some feedback. So see you next week with the next lecture. Have a good one. Bye.